Hello, this is a video supplement to the article Elemental Vacancy Diffusion Database from High-Throughput First Principles Calculations for FCC and HCP Structures, published in the New Journal of Physics. The authors are Tom Angsten, Tan Mayeshiba, Henry Wu, and Dane Morgan, all from the Department of Material Science and Engineering at the University of Wisconsin-Madison. This video will be presented by Henry Wu. In this article, we study properties of elemental systems and metastable crystal structures. Specifically, vacancy formation and migration energies are calculated for elements in the FCC and HCP structures. For many elements, these two structures are not their natural ground state crystal structures, which makes it all the more valuable to obtain this database for thermodynamic calculations. To compute atomistic properties, we utilize density functional theory. DFT is a quantum mechanical computational method to model the electronic structure of atomic systems. The more than 100 systems calculated in this article were all automated using the Material Simulation Toolkit, a Python code package developed at the University of Wisconsin-Madison. The vacancy formation energy is the energy needed to create a single empty lattice site in the bulk crystal. This energy is related to the cohesive energy, or binding energy to bring together free atoms and form a bulk solid crystal. Here we plot our calculated vacancy formation energy and calculated cohesive energy for elements in the FCC structure on the left and HCP on the right. Symbols represent the natural ground state crystal structure for each calculated element. We see that naturally BCC, FCC, and HCP elements show a nice correlation between their vacancy formation energies and cohesive energy, while elements with less common structures do not correlate as well. The vacancy migration energy is the energy needed to move the vacancy to another lattice site. This requires a lattice atom to move in the opposite direction of the vacancy. The motion of this atom distorts the surrounding lattice sites, and the energy needed for this distortion relates to the bulk modulus, which is the measure of a crystal's resistance to uniform elastic compression. Again, we plot FCC on the left and HCP results on the right, comparing vacancy migration energy versus the bulk modulus. Here we see that the vacancy migration energy correlates very well to the bulk modulus for elements with both common and uncommon structures. With our large collected database, we set out to create a predictive model for FCC vacancy migration. We utilized a strain energy model to relate the vacancy migration energy to the lattice constant and bulk modulus. This plot shows our predicted vacancy migration energy on the vertical axis compared to our calculated vacancy migration energies. In summary, we have calculated a large database of vacancy properties for elemental systems in FCC and HCP crystal structures. We have developed a model to predict vacancy migration energies using physical properties. All calculations were automated and managed by our Material Simulation Toolkit, MAST. If you're interested in this article, please follow the link below the video. On behalf of all the authors, thank you for viewing this video supplement.